Welcome you all to this talk on a very important concept of calculus, which is known as limits. Now, I'll advise you to pay proper attention to the concepts here because the concept that you acquire here will be used throughout the discussion of calculus. Concepts like continuity, differentiability, integration, and so on. So let's straight away come to the concepts. I write y as a function of x. Now, before I proceed, uh, you must understand that whenever we say y is a function of x, that means we are dealing with a real valued function. Y is a real valued function and its domain consists of real numbers. Now, every time I write a function, I'll not be mentioning that this is a real valued function and domain consists of real numbers, but you have to keep that at the back of your mind. Now, I'll take a specific function y to be 5x. Now, I make a sketch of this. This is the rough sketch of the function y equal to 5x. Now, put the value of x to be 5. Now, what is the expected value of y? So, this is simple. As you put x to be 5 here, it gets multiplied by 5 and the value of the function turns out to be how much? 25. So, this function is exactly defined. There is no confusion. And when you put x to be 5, you get y to be 25. Now, does it make a difference if you come to 5 from right side or you go to 5 from the left side? Will it make any difference? No, it will not make any difference. You go to 5 from this side, still the value of the function will reach 25, and if you go from this side, still the value of the function will reach 25. But in the limit terminology, there are different ways to write that. If you reach 5 from the right side, then you write limit x tends to 5 plus. Limit x tends to 5 plus the value of the function is 25. That means that you are going to 5 from the right side. You give values to x such as 5.5, 5.4, 5.3, 5.2, so on, and you reach till 5. The function reaches the value 25. But we write it as limit x tends to 5 plus the value of the function is 25. Now, if you reach the value 5 from the left side, then you write limit x tends to 5 minus fx, but in this case it is still 25. Now, this means that you give to the function values 4.5, 4.6, 4.7, so on, and you reach 5. Starting from values to the left of 5, and you reach 5. But the function still reaches where? The function still reaches 25. But in symbolic notation, it will be limit x tending to 5 minus, and the function will be getting the value 25. Now, in this case, the function was defined at 5. Now, let me take another case when the function is not defined at a certain point. Suppose we have got a function x square minus 4 upon x minus 2. Now, see carefully this function. In the numerator, you have got xy minus 4, and in the denominator, you have got x minus 2. Now, definitely, in this function, x cannot be equal to 2, because if you put x to be 2, the denominator will become 0 and the function will become undefined. But suppose x is not equal to 2, then you can simplify this as x plus 2, x minus 2, and in the denominator x minus 2. So assuming that x is not equal to 2, so these two amounts are non-zero, you can cancel it, and your function simply becomes x plus 2. Now make a sketch of this. So roughly it is something like this. This is y equal to x plus 2, or you can also say that this is the original function, x square minus 4, x minus 2, provided x is not equal to 2. So what is different here is that there is a gap in the function here. When x is 2, the function is not defined. If you take exactly x to be 2, the function is not defined, and the function is defined at everywhere else. Now, does that make any difference to the discussion of limit? The answer is no, it does not make any difference, because if you come to this point 2 from the right side, your function still moves to 4. You get my point? No matter the function is not defined at 2, but to the values close to 2 on the right side, the function values are close to 4, and to the values close to 2 on the left side, the function is still close to 4. So here, if you move to 2, limit x tends to 2 plus, or limit x tends to 2 minus, your function goes to 4. Now the function is not exactly defined at 2, but the function has got the tendency to move towards 4. So we will say that the limit still is there and the limit is 4. So what do we understand from all our discussion? That the function may be defined at a point, the function may not be defined at a point, but the function has the tendency to move towards a value when you assign a particular value to the independent variable. Like in this case, when you move your values to 5, the function moves to 25. Here you move your values to 2, the function moved to 4. The difference was that here the function was defined at 5 and here the function was not defined at 2, but that didn't make any difference to the value to the discussion of the limit. Now in both the cases, the functional value seems to be moving towards some value, and that is called the limit of the function. Now we'll continue our discussion about the limit with the help of the graphical analysis. Now I gave you two functions, but let's do some more graphical cases. Suppose I take a function y equal to sine of x. Now this is a very basic function in trigonometry, and I hope all of you are familiar with this. So if we make a sketch of this, now this is the x-axis, this is the y-axis. So as you know, sine is a periodic function. If you take the value of the angle or x value to be minus pi, So let's say here it is minus pi by 2, this is 0, this is pi by 2, and this is pi. So the function will go like this. Okay. Now, sine is a periodic function. It attains the value 0 here. It goes to, suppose this is minus pi by 2. This goes to minus 1. That reaches 0, goes to 1, and then again goes to 0. Now, suppose I am checking the limit x tends to 0 sine x. Now, this is a question for you, that suppose x goes to 0, where does the function go? Now, what is your answer? Now, you cannot jump onto any answer. You have to investigate. Now, x goes to 0. So, do one thing. You move to 0 from this side and you move to 0 from this side. As I explained the concept of the right hand limit and I explained the concept of the left hand limit. So, you see that when you move to 0 from the right side, as your graph suggests, that the function goes to 0. Now, if you move from the left side, then also the graph suggests that you go towards 0. Okay, I repeat. You see here from the graph, if you go to the value 0 from the right side, the function seems to be moving towards 0. And when you go from the left side towards 0, the function still is moving towards 0. So no matter from which side we approach, the right side or left side we approach 0, the function seems to be taking the value 0. So here the limit would be said to be 0. Now this is one example. Let me give you another example, a slightly complicated function. Limit x tends to 0, x sine 1 by x. I'm just trying to make the concept more clear. We are not into any technical discussion still. I'm just giving you some graphs and trying to make you convinced that just by taking a cursory look at the graph, you can understand that the function is approaching some value. So I'll make a graph of this function. This is a very interesting behavior on the part of the function. Now, if you make a graph, you have to take these two lines. This is the line y equal to x and this is the line y equal to minus x. Now, the behavior of the function is like this. The function behaves like this. So, my question was, what is the value of the limit of the function when x goes to 0? Now, again take a look here. This is the point 0. Now, you move to 0 from the right side or you move to 0 from the left side, as it is amply clear from the graph that no matter you move to 0 from the right side or you move to 0 from the left side, the graph of the function suggests that the function is moving towards 0. So here you can write that the limit of the function is 0. So two cases. In the first case, limit of the function, limit going towards 0, no matter you move to 0 from right or from left. And here also the function seems to be going towards 0, no matter you move to 0 from the right or from the left. So just by taking a look at the graph, you come to realize that there is a limit and you can locate the limit. Now, I explain another case which is very interesting, where you can use the diagram. Now, you cannot tell me the limit just by taking a look at the diagram, but you can analyze the diagram and slight calculation on your part will let you reach the value of the limit. Okay. So limit x tends to 0 sin x upon x, I write like this. Limit x tends to 0 sin x upon x as the greatest integer function. Now, I will assume that you know what is the greatest integer function. Uh, so, let me make a diagram of this. Now, you see there are two functions which are involved, sin x and x. So, I've already made a diagram of sin x. So, I'll again make it. You know that sin x goes like this. This is your sin x. And then I'll make y equal to x. Now, this is x. This is y equal to x, and this is sin x. So, this is your graph. Now, only your graph will not tell what is the value of the function. You have to slightly think about that. As I was telling previously, that combined with the graph, you have to put up some logic, and then you will come to know what is the limit. Okay. Now, limit x tends to 0. So, you move to 0 from the right side and you move to 0 from the left side. Now, see the behavior of the function. When you move to 0 from the right side, what do you find? You find that sin x is less than x. Sin x is less than x because in the first quadrant, you see that the function sin x lies below y equal to x. Now, this you can prove once you study the Lagrange mean value theorem. There you can have the formal proof of that. But here I am not going to give that proof, but simply tell you that just to take a look at the diagram and you see that sin x is less than x. So, what will happen? This means that sin x divided by x is less than 1. Now, this conclusion you get from the graph. Okay? So, sin x upon x lies between 0 and 1. Okay, but this is the greatest integer function. So, any value which lies between 0 and 1, if you take its greatest integer function, that will become 0. So, what is the meaning? That we go to 0 from the right side, the function moves to 0. So, we combine graph and a little bit of analysis. Now, let's see from the left side. Now, what you find here? You find that sin x is greater than x. Okay? Because both the values have become negative. So, sin is lying above that, right? The sign is small in magnitude on the negative side of the number line. So, sin x is more than x. But both are negative numbers, mind it. So, when you divide sin x by x, the inequality will change. Because you know that whenever you divide by a negative number, the inequality changes. So, again it becomes less than 1. Now, we take the greatest integer function, this will become 0. So, you see how interesting it was that we analyzed the behavior of the function on this side of 0 and on this side of 0, and we got the conclusion that on both the sides the function seems to be converging to the value 0. So, here also this limit is 0. So, we are still continuing with our graphical presentation. I explained you 3 cases where directly by taking a look at the graph or taking a look at the graph and doing some logical analysis, you reach the conclusion that the limit existed in all the 3 cases, and we easily found that. Now, it will be useful now to consider some cases when limit does not exist. So, till now we have been discussing that limit exists. So, let me show you again. I'll continue with the graphical analysis. That I'm going to take 2 cases when the limit does not exist. Now, first of all, let me take a function which is known as the greatest integer function. You are familiar with this function? This is called the greatest integer function, or this is called the floor function. Now, I'll make a diagram of this. This is x-axis, this is y-axis. Let's take some values 1, 2, 3 here, and 0, minus 1, minus 2, minus 3. Now, you know the diagram of the greatest integer function, that it goes like this. Now, let me use some other color for your benefit. The greatest integer function is like this. I'll take here 1, 2, 3. Minus 1, minus 2, minus 3. This is the greatest integer function. Now, what is the speciality of this function? That if you take some value between 0 and 1, excluding 1, it will remain 0. At 1, it jumps to 1. Then from 1 till 2, excluding 2, it remains at 1. And then it jumps to 2, goes to 3, jumps to 3, goes to 4, so on. So this is the greatest integer function. Now, I'll check its limit. Limit x tends to 0 or 1 or 2 or minus 1. You get my point? That means I'm checking the limit at some integral value. I'm not taking the limit at non-integral values. I'm taking the limit at integral values. So let me check this at 0. Now, as our discussion goes, we can go towards 0 from the right side, or we can go towards 0 from the left side. Now, what do we find from here? That if we go to 0 from the right side, the value of the function is how much? 0. But if you go to 0 from the left side, then the value of the function is minus 1. So, this is a little different in this case. Till now, you went from the right side or you went from the left side. In both the cases, the values came out to be the same. But here, what do you find? That when you go to 0 from the right side, the value of the function is 0. And when you go from the left side, the value of the function is minus 1. Similarly, check it out at 2. Okay, you go to right. You go to 2 from right, the value is 2. But you go to 2 from left, the value is 1. So the values diverge. You go from right to the value or integral value, or you go from left to the integral value, the value of the functions differ. That means the limit does not exist. So this is one case. Now I'll give you another case where the limit does not exist.